Hi everyone, another video that need not necessarily be in the lecture series, but I want to point out an interesting consequence of Faraday's law that is not something that's exactly obvious, but it's connected to something I mentioned earlier. So with Faraday's law, we know that when we change the magnetic field, it induces an EMF because of the Lorentz force law. Now, the weird thing about this law is that that electromotive force is actually circular, right? It drives current around the ring. Now, the problem with this is that that implies that there is an electric field that is circular in nature. Now, in the video when we talked about curl and divergence, I mentioned the fact that Coulomb's law implies that the electric field is pure divergence. There is no circulation in the electric field at all. Faraday's law actually violates that assumption. In a very fundamental way, Faraday's law is incompatible with Coulomb's law. And so this is really the first moment where we start to see the fact that, remember, this is all predicated on this idea that two parallel lines of current attract one another. That single fact pushes against the foundation of the electric force. And so what we have here is we can recast Faraday's law. I don't expect you to follow exactly what this means, but remember, this symbol over here represents the circulation, the curl, how much the electric field is twisted, and we had a 0 on the right-hand side of this equation. Faraday's law puts a changing magnetic field on the right side of that equation, and essentially what this is saying is that when the magnetic field changes, we get a twist in the electric field. Now, not only does that violate Coulomb's law, but kind of in a mathematical sense, violates the foundation of the definition of electric potential. We didn't focus on the fact at the time, but I mentioned how when we talked about energy, energy is only possible when we have conservative forces. In the same way, if we have an electric field that's not conservative in the sense it has no circulation, then we can't really define an electric potential. In other words, Faraday's law really makes it mathematically, it violates our derivation of the electric potential. Now, it's possible to kind of recover from this, and that's what this formula down here represents. This is the modification for the electric potential. Remember, this was the definition we had originally, where the electric potential difference was defined by the electric force times the distance traveled. That was what we used to define the magnetic potential initially. This is how we need to revise the definition to account for Faraday's law. And it's not obvious that this is possible, and in fact it's very fortunate that there actually is a way to recover from this. But nonetheless, here it is. And what this represents, the A is a new symbol. It showed up on one of the slides in the previous videos. I didn't mention it at the time, but this is really something called the magnetic potential. The magnetic potential is possible because the magnetic field does no work. And so even though the magnetic field is a vector, we can create, even though the magnetic field has curl, in fact it's all curl, even though that's true, we can still create a potential in a mathematical sense. The problem with this A is that it is itself a vector. So there's really no mathematical ground to be gained. You turn a vector into another vector, so what's the point of that? Well, here is where it starts to show up in kind of a technical, mathematical an abstract way. We won't use this formula, but I just think it's interesting how this very simple and innocuous fact of parallel lines of current attracting one another really starts to infect everything we've learned about the electric field so far, and we are being forced slowly but surely all the way to Maxwell's law and Einstein's theory of relativity as a consequence.